Hello, everybody. Thank you for joining the webinar about human factors and user experience provided by Logistics. My name is Tobias Komischke. This is a repeat session from last week. We experienced some noise problems back then. I hope today the only thing that you hear is my lovely voice. And we will provide links to this session that you can also access the recording of the webinar after the fact. So the presentation is called Human Factors and User Experience. For everybody who doesn't bring a lot of time, here's the executive summary, which says technology advances, people stay the same. So we as humans, we are what we are. We have, our brains hardwired. And so it's a challenge that with technology being advancing so fast that we can keep up with that. And so the whole presentation is about human capabilities, human limitations, and what those mean for the user system or user-computer interaction. A little bit about myself. I'm the Director of User Experience at Logistics. I work in services. I studied that UX stuff, and I have more than 12 years professional experience in that field. I worked in research, I worked in development, I worked as an in-house consultant, I worked for external consulting. And the very first thing I've ever seen about the topic of usability engineering, as we called it back then, was that slide here about this guy finding himself on a strange planet, talking with a very strange life form. And that life form asked him, think back, which keys did you press? So I think it's been a while that I've seen this slide, but it's still so relevant because we have very powerful systems out there, but we do want to avoid situations like those where you don't know what's happening, you don't know what you can do next, you don't know where you come from. And not only that, we want to make it very enjoyable. We want to support certain objectives that people try to accomplish with the system. And all this kind of is wrapped up in this little image here that I really like. So working at Logistics Services means that we have a lot of customer engagements and customer interactions, since we do everything from the early user experience design all the way through the implementation of front ends and everything in between. We work across industry, we work across platform, we do consulting, we do training. And because of that, we always hear a lot of questions and uncertainties from our customers regarding the user experience, saying, oh, what is the best way to do A, B, or C? Or would people be able to understand X, Y, and Z? And so over the years, we just collected those kind of questions, and today want to share some of them that really revolve around, okay, what does it mean for the user experience if you really consider what humans are good at and what are they bad at? So, but just to clarify what I think user experience is, because obviously there's tons and tons of definitions out there. I like this one the best, which says the envisioned, expected, or actual user experience of a user interacting with a technical product. So it's not only the actual experience, it's also the envisioned and expected one, which talks a little bit towards the fact that it's really important to anticipate the future experience in design time. Well, what it also means is that no matter what you do, no matter if you invest in UX, if you care about it or not, if you incorporate it into your development lifecycle management or not, there will always be an experience for the user. And obviously, we try to shape that. So the bottom left image here is where the target is. We want to have people that have a blast in interacting with the technical system. They should be able to accomplish their goals, but they should also have, a joyful experience. So that's the target. Now somebody has to create that though. And so here on the right-hand side, this poor developer struggling with, not only providing all the functional requirements, but also making it a good experience, an anticipated experience for those developers, for business analysts, for product managers, for project managers, for other UX design professionals. We provide these kind of webinars because we think we have something to share in terms of experiences and best practices. Now, this specific webinar here is about human factors. And there's a discipline called human factors engineering, which is the science about the human characteristics, what the capabilities of humans are, what their limitations are, and then the practice of applying that knowledge to optimize the interaction between a human and a computer or a system. So these disks that you see here, and I hope you see them well through the streaming, these disks appear to be spinning while they don't. It's just a static image, but they give an impression, a perception of movement. And that's just talking towards the fact that oftentimes we don't even know exactly why something is happening in our brains, but we know that they are happening. And sometimes we can make use of that, sometimes we want to avoid that, but it's good to know about these kind of things that happen in our brain, because obviously user interfaces are very graphical, and it's good to know what the capabilities and limitations of users are. This example here, and if you joined last week's webinar, you already know the solution of that. This is an effect that's called change blindness, which is we flip here between two different versions of the same photo, and a very crucial detail of that photo changes. One time it's there, one time it's not. Can you say what that is? And most people really have a difficulty to actually see the difference, and that's what it's called, why it's called change blindness. So I'll give you the solution. The change is that on one photo you see the turbine, the engine, and on one you don't. But for the first time, if you don't know that solution, most people do not see the difference. And it's just another, a casual example of, well, knowing that there's a phenomenon called change blindness may have some impact on the user interface design. Because what is it if you have a supervisory control system or any kind of real-time system that alerts you about something, maybe an alarming system or on a property management system, an intrusion alert or something. And what is it that prevents people to actually see that there's a pending alarm, which may be really important to know, but people just don't perceive it the right way. So knowing that these can be challenges, you have a better idea on how to design it, that you actually see something. Another quick example, since now we have the 100th anniversary of the sinking of the Titanic, sank in 1912, is the topic about vigilance. So we do know that we have limitations as humans. We have known this for more than 100 years. But 100 years ago, with the sinking of the Titanic, it became a little bit more emphasized that this is really a problem, since so many people died in the incident. And obviously the sinking had many causes. But one of that was that issue about vigilance, which vigilance means the sustained attention for low probability events under monotonous conditions. Meaning that in 1912, they had two people here on the crow's nest and on the top of the ship, and they were just there to see if there are icebergs ahead, and then if there's an iceberg to warn the bridge so that the ship can steer around the iceberg. So what happened obviously in that night is that they saw the iceberg really late in the game. The ship could not go around the iceberg, and it hit the iceberg and the ship sank. Many people died. So it became apparent that these guys here were on their shifts for more than 2 hours already. It was night. It was not the best, visibility conditions. And so was that an issue that, they were already tired? They, may not be on the top of their game. It was a very harsh environmental factor involved. Well, it turns out, yes, that was one of the factors. They could have seen the iceberg maybe quicker if they were at the beginning of their shift, if they had been more alert. Now, 30 years later in World War II, there was a similar issue, but this time actually the iceberg shot back. In other terms, this was naval warfare, and it was about detecting enemy warships that now obviously shot at you, different to the iceberg. It just was waiting for you to hit it. And even though the people on the ship in the lookouts knew that it was live, it was really adamant and important to see the other warships, they oftentimes couldn't see them even though they were clearly there, just because they were tired. And so we see the same problem today, that because of vigilance reasons, people cannot detect something that's clearly there. And obviously the TSA issue about how easy it is to smuggle weapons through the scanners here is to a high degree attributed to the fact that these guys here just after a certain amount of minutes are not at the top of their games anymore. You see this here on the chart on the left, that the percentage of correct detection of something goes down a lot over time. So here, after 20 minutes of doing, for example, a task like this, to look for something that is really low in probability and it's a monotonous condition, after 20 minutes, the positive detection rate is only at 70%. So that's a real problem, and it's just the way we are as humans. It's the way we are wired in our brains. There's nothing fundamentally you can do about it. Obviously, they try to switch these guys here, in fast paces so that you don't get to the 20, 30, 40 plus minutes range here. But the way that this phenomenon is occurring is just natural. It's what we humans bring to the table. So in the 50s then, people like Fitz, and that's the same Fitz that came up with Fitz law, came up with this, systematic approach to say, well, if we know we have capabilities, but we also have limitations, let's come up with a list that says, well, humans are better at certain things, but machines are better at certain other things. Back then, they called it MABA lists. And so it was men are better at it, machines are better at. They didn't, not for obvious reasons, but they did not consider women back then. That's why it's called men and not, Haber MABA, humans are better at. And some of these lists here obviously change. The first one here under men are better at detecting small amounts of energy or cues. With sensor technologies, I think in a lot of cases machines are better at that already. But some things are still the same, and I think for a very long time will stay the same, including here, humans are better at reasoning inductively, like generalizing things, while machines are better and much faster in reasoning deductively. So that's, also nice because it helps you to say, well, what should the machine do, or what should the software be responsible for, and what should be the humans responsible for. So we can look at ourselves, our way our human cognition works, as we look at a spec at a machine. So, we have different processors that do different things, cognitive processors, motoric processors, perceptual processors. They have certain, cycle times. They have certain pathways from the sensors to the brain. And we have all kinds of different memory types. And, just talking about this memory a little bit. So if you are, experienced in e-commerce and you like to shop on e-commerce sites, maybe you shop at Amazon for a book or something, you know that it's a very bad approach of e-commerce sites to require you to memorize, for example, an order number, right? You have these endless numbers of, random strings that may be like 10 or 11 or 12 characters long. It's a very bad practice to require the customer to remember that and then to enter it on one page and then maybe another page further down the road. Why that is? Because our working memory has only a capacity of 5 plus minus 2 chunks. Chunks are, meaningful groups of items. But since an order ID number string is very arbitrary, because there's no semantic in there, it's really hard to keep this in working memory. So you could argue, well, if it's just working memory, why don't we put this into long-term memory? Because there we don't have a retention period of only 7 seconds like in the working memory, but it's infinite. So we can memorize this forever. Isn't that cool? So, why can't people just put the order ID in the long-term memory? Well, it's very, very hard because the content in long-term memory is semantically coded. So for an arbitrary number, it's very hard to do this because the arbitrary number, it's not semantically coded, but just arbitrarily coded. So all these are reasons to say, well, there's a good reason that most good e-commerce websites out there will not require you to memorize any arbitrary string of characters. It's taken forward to you. It's defaulted in the fields as they are needed, and they try to support you in that. So obviously, there's a good reason why we have graphical user interfaces today and not these kind of line entry field-based commands that you see here on the left-hand side. Because, as I just mentioned, transferring items from the working memory to the long-term memory is effortsome and it's also error-prone. It happens that people are much better at recognizing things than recalling things. So here, on the left-hand side, people would need to recall the semantic structure of, a functional input. So, for example, here, this is like, to put a text file into a zip file. I need to know what the semantic is and what the structure of that entry is. I have to recall that from my memory. On the right-hand side, it's the other pathway, which is recognizing things. So I have menus here, the context menu that tells me, among other things, for a selected item, I can actually do zipping, and in there I can have different ways to create a zip. So this is just seeing what's there. It's recognizing something that I may have seen before. This is much better for a human. And that calls for action, which is, it's always good to try to externalize memory. Don't require people to memorize anything, but put that on the system side on things and show things to select from rather than expecting people to recall things from scratch. And this is like nicely shown here in the evolution of our user interfaces. That's why graphical user interfaces are so strong and powerful. Another very nice phenomenon that we see with us, the humans, is that we have certain features in visual scenes that really pop out at us. Why? Because certain elements stick out because they are very different from other elements. These are called the so-called pop-out features. And they're very powerful, and we can use them very nicely in UI design. So pop-out features are those, for example, intensity. This one stroke here is lighter than the others, so it sticks out. This one here has a different hue. This one here has a different weight. This one here has a different orientation. And although there are so many of those elements, this one sticks out very clearly because it's different from all the others. And this works for all kinds of different attributes, including blinking and intersection, or here only one is closed, the others are open. This one here has a little curve. Here the density is higher than the rest. All this works very nicely. We also know this from more natural scenes, like outside of the software. So, for example, here in a conference, this sign here that says you can get food here sticks out very well from the background because of its color, its shape, its position, and obviously that's important because it's good to know where there's food to grab. So this mechanism of this pop-out features is used in hospitals, for example, by radiologists that do all these medical images through your body, and then they have like 600 slices of your body, and they try to find maybe a tumor. And this is done by the same mechanism. You can have the system help you to detect a tumor because the system will use those kind of pop-out features and say, well, a tumor is visually something that's different from the rest of the tissue that you have in the body slice. And so the software algorithm that a radiology would use uses the same principles. They would look for different colors, different orientations, different closures, different densities, and by that help the radiologist to find a tumor. Now, it sounds a little bit theoretic, but let me give you an example of how you can use that today after this webinar in your development. So these kind of saliency models that can be used that kind of have these pop-out features intrinsic, we used in a development that we did where we had a system and we had a certain scene where we overlaid a dialogue on top of a background, and then we had some information here, like shown here. And we did some usability testing on that, and we realized that a lot of test users struggle to see this close button that you see here on the top right of the screenshot. And so, well, obviously, if we now know that there's things like pop-out features, we know that there may be different reasons why people struggle to see this. But we actually ran this through a saliency model that you can also use, and that is available on a website called fenggui.com, kind of like feng shui, but just replacing shui with GUI for graphical user interfaces. It's a service-based website. You can pay money for a number of those kind of heat maps, but they allow you to do one heat map a day for free. So you can upload an image and can have them analyze that image in terms of the salient parts based on those pop-out features. And so when we uploaded that screen here, this is the heat map that we got out, which shows where people would look in the first kind of third second of exposure. So these are the most salient parts of the screen here. And you see here, it's the center because of the position. It's also the shape. It's also the color treatment. So this central image here draws a lot of visual attention. And then it's the beginning of this text paragraph on the left and here on the right-hand side. But you see here that the close button here doesn't draw any visual attention. So that's very nice to show that actually with an algorithm. The question now obviously is, what can we do about that? So how can we make that close button more prominent, that people actually see it and can act upon it? Well, we could change the size. We could just make it larger. We could also change the position of it and locate it a little bit more towards the center of that screen. Or we could also use blinking or flashing, or we could also use a different color treatment. There's different ways. And what we decided to do was we just changed the color a little bit. You see this here. We just chose a brighter hue. And that's all we did. We didn't want to change the position nor the size. And then we did another round of usability testing for the whole application, and always checked back if people now can see the close button, and turns out now they can see it. And just to be sure, we also ran it to the same algorithm again on fenggui.com. And what happens is now this time even the algorithm picked it up and said, yes, it's salient enough that people would see this. Obviously, still, it's not the most prominent part. No, it should be the most prominent part because it's really the content here in the middle. But now it's salient enough that people see the close button. So that's really nice. And again, the advantage against, for example, an eye tracking system is that this is very fast and this is very cheap. An eye tracking system costs like $30,000, $40,000 if you actually buy that. If you outsource that to a service provider, you still pay a lot of money for that. and it will take a while to bring back the data. This here is for free if you only do one a day on this fengui.com website, and it's very, very fast. The difference though is the advantage for an eye tracking system is that this here only models like the first, third, second. I mean, anything beyond that, when people start to wander with their eyes, this model here breaks down. For that, you actually need eye tracking. But just to see what are the salient parts and what are the parts that may not be picked up, this is a very good way to do that. And it's based on really human factors. Another area of consideration is data visualization. So we often talk with customers about how to visualize data. Obviously, that's a good thing to visualize data because there's something called the pictorial superiority effect. Something that is visual is superior to something that is shown abstractly in ASCII, like in text and characters and numbers. But the question is always, there's so many different ways to visualize things, so how should we do this? There's many, many different chart types, for example. So what chart type is better and what is worse? And so research says that there's a spectrum, and you see this here going from easier to harder. Easier and harder meaning here, how easy and hard is it for a human to interpret a certain chart? How long does it take, and how accurate is the interpretation of that chart? And so research is saying that the easiest way to the easiest way for the end user to show data in a chart is if the chart is based on a one-dimensional axis. So this is a column chart, and the same is true for anything that is like based on a one-dimensional axis. Column chart, bar chart, all this is good. It's very easy to interpret by humans because we are pretty good in estimating heights in that respect here. It's a little bit harder to interpret angles like you would have to do here on a pie chart. It's even harder to interpret areas. I'll give you an example later. And the hardest thing is to actually try to interpret volume because now you talk about three-dimensional data. It's very hard. And so this is just a finding from research. I'm not saying that pie charts are always evil or that 3D pie charts are always evil. I'm just saying if you want to really consider the ease and accuracy of the interpretation of a chart, the top ones are easier than the bottom ones. That's all I'm saying. And an example here is this famous one that Steve Jobs showed years ago, which shows market share data of smartphones. And he used a 3D pie chart that was a little bit tilted backwards, which the funny effect that the number one segment here, the blue one, is RIM, Research in Motion, that is BlackBerry. And then by the number, the next largest segment would be this purple one here, 21.2%. which is all the others combined. But by tilting the 3D pie chart, they actually made it appear that the green segment here would be second largest of those segments, even though by number it's only the third. And so, since green is Apple, and this was an Apple presentation of Gartner data, it brought him a lot of heat because people were saying, they're manipulating the marketplace here by doing this. And if you think about it, is there a compelling reason to show this data on a 3D pie chart? There is no compelling reason because there is no third dimension. This is the data that is, and why would you introduce a third dimension if there's no reason for it other than maybe for the sex factor or maybe, I don't hope that they wanted to actually manipulate investors or something. So based on this here, I'm saying that, areas are also very hard to interpret. Let's look at this image here of Mickey Mouse. Most people have a very hard time to estimate how much times is the right ear larger than the left ear in terms of area, or how much larger is the face of Mickey than the right ear. People typically underestimate the size change or the area change when you change the diameter or the radius, because it changes quadratically. Turns out here in this example, Mickey's right ear is twice as large as the left ear. And people always underestimate that. People may think, well, maybe this ear is a third larger. No, it's actually twice as large as the left ear. And the face is twice as large as the right ear and 4 times as large as the left ear. So the message here is, if you really want people to really understand and grasp the data, don't rely on an area chart that would convey that meaning. So if you really have to provide this in a bubble chart, for example, then you have at least provide the actual data label, because otherwise people will just not be able to interpret it the right way. So I wanted to talk about 2 very fundamental aspects of the user experience. One is color and one is text, and talk a little bit about, what is it that we should consider for color, and what is it that we should consider for text. So why is color important? Well, first of all, we talk about graphical user interfaces. So color is part of any graphical scene, even any natural scene. It's very rare that we see anything that's completely colorless and it's just gray and or black or white. Usually color is embedded in any kind of visual scene. So we're very used to see colors. We're very sensitive to see colors. We're very good in discriminating colors against each other. On a UX perspective, colors have the potential to either boost or wreck the user experience, because we can use colors for a functional aspect. For example, to steer visual attention. I just gave you the example of the close button that was more visible just because we had a more prominent color than before. We can use color for the appeal, to establish this tie, the emotional tie between a user and the system, or a company and a user. So using color stereotypes like there's warm colors, there's friendly colors, there's cool colors, there's cold colors, all that we can use for this appeal. And we can use color for branding. A lot of, if not all of the brand treatments that you see out there in terms of logo treatments, they all more or less have color. And so we can use that to communicate value and alignment of the software with the overall corporate messaging. And the most questions we always get about color treatment is, oh, we hear so much about people are colorblind, or we don't know what that means, but what is it that you have to do for mitigating color blindness? And I even hear on conferences for usability the most bizarre numbers on color blindness that make it sound like every other person out there is colorblind. So I just wanted to set that record straight a little bit and explain a little bit what color blindness means and what it means for the user interface design. We perceive colors as humans through 3 types of color receptors, and these are called the L, M, and S cones. And they are most receptive to different parts of the visual spectrum that goes from about 360 nanometers to almost 700 nanometers. And so the L cones are called L cones because they're most receptive for the long range here on the upper end, the M more in the medium range, and the S cones for the lower range. So we have these 3 types of color receptors in our eyes, and there may be deficiencies on those receptors. And depending on the deficiencies, you may have a distorted color perception. Interestingly, most people are not even aware that they may have a color deficiency, a color perception deficiency. So when you go to the optometrist or to the eye doctor, they will show you those kind of plates and ask you, hey, what do you see? So I ask you now, what do you see? Do you see larger geometric shapes, and what are those? Most people will be able to see a large yellow circle, and it's positioned here. Now, if there's any, and based by the number that I see here attending the webinar, we should have several. If there's anybody who is red-green colorblind, and it's the most frequently occurring color perception deficiency. Those people would not see anything else but this large yellow circle. In fact, there's another shape which is a square, and it's here. So if you don't see a square that looks like reddish-brown, then you may have an issue with perceiving red-green. And here you see a list of all the things that can go wrong with your cones, and then you know what the effect is. But just saying, you could have a complete loss of a cone type or all cone types, or you have just some deficiencies. But if you look at the numbers here, like the incidence rates here, you see that in the end, we talk about women having hardly any issues with color perception deficiencies. It's mainly men, and it's only 8%. So 8 out of 100 men have some form of color perception issues. And what they have issues with, based on those numbers, is mainly a problem perceiving red and green. That's it. So it's red-green color blindness. Anything else is really, really rare. You see this here, the blue-yellow color blindness. It's 2 out of 100,000 men for this cone type, and 2 out of 100,000 men for this deficiency. So it's combined 4 out of 100,000. It's very, very rare. And also the total color blindness, it's 3 out of 100,000 men. So it's very rare. So I'm just saying, if somebody is concerned about color blindness, it's men, and it's about red-green color blindness. So what does it mean for user interface design? This is a very old slide. This is what our website looked like 4 years ago. And we just launched our new website. In case you have not seen it, go to infostatistics.com, and it's really nice and awesome and great looking. But at one time, it looked like this. And back then, I was just showing a couple of our guys the effect of color deficiencies. So this was the website. You see, you know, it's sort of text, it's imagery on it. We have lots of colors. So you can simulate what that would look for somebody who suffers from color blindness or color perception deficiency through tools. If you just Google color blindness simulators, you will find tons and tons of tools that allow you to do that same thing. So here, this is a simulation of the red-green blindness based on the L-cone problem. So again, it's 2% of the males, and it's 0.04% of females. And you see the effect here that we lose the reds and the greens, but that's about it. We can still read things. We can still see that, oh, this is an image about some column charts and a sprinter. We can still see that here's a color wheel that shows different colors, even though we cannot see red and green on it. So the effect is really not a lot. I mean, this is still functional. You can still see everything. Now we can do the same thing for the M-cone. And since the two sensitivity curves are so close to each other, there's hardly any difference between these two. You can still read things. You can still see things. If we now do the blue-yellow blindness simulation, you see that now we have filtered out different other colors. So now we see the red. The green turned more into, like, you know, a grayish hue. It's not really blue. And again, I can still read everything. I can still see the picture. I can still see that this is a color wheel. Even if I simulate the total color blindness, which is very, very rare, I can still see things. So does that mean that color blindness doesn't play any role whatsoever? Well, it depends on the content. For things like this, it's really not that important. But what about scenes like this that I just grabbed from the internet, where we see some charts and gauges that show some financial data? So here we rely heavily on color to understand what we see, because there's no legend here for these two guys here. So we would not even know what this is unless we look at the colors. So it says year-to-date sales, and you have a red range and a yellow range and a green range. So we know from our experience that red is not a good thing. So even though the pointer shows here that we are in the red range with the year-to-date sale. We obviously want to get to at least the yellow or the green state. So we just understood the whole meaning of this purely by color, by nothing else than that. So now what if I take away that color information and simulate again the red-green color blindness, and in this case for the L cone? Now all of a sudden I lose that color coding, that meaning of color. So what is this? This is brown. It's like, awesome. What does it mean? I don't know. I also lose the difference pretty much between the yellow and the green. They both look like a brownish yellow to me. So now this talks to the fact that depending on the content of what you want to show, it may be important to actually work on a good way to not only single code information by color, but to multi-code it. So here there could have been a legend, there could have been a label saying, safe range, intermediate range, and good range, these kind of things. Lacking all those, it may be really hard to interpret that scene. And the same for the N cone, and the same for the S cone. S cone, now we have our red area, the red range back, but we still made it pretty ambiguous here to understand what does that range mean, what does that range mean here. And obviously the same for the total color blindness. So the message is, don't rely on the color information alone if you want to code meaning into a visualization. This one here is a screen done by IDERA. They won the Nielsen Norman Usability Award, I believe in 2008, for that system. I think it's a supervisory status indicating system that shows whether servers are up or down. I'm not really familiar with that. I just knew about it because they won that usability prize. And maybe one of that reasons for winning that award is that they not only double-coded their information, but they actually triple-coded things. So you see this here. They have one visual indicator for a critical state, for a warning state, for the OK state, and then they have something else. This is maintenance mode. But see that they don't only use color to code this. So obviously they use red for critical and yellow for warning and green for OK state, like the regular traffic light color coding. But on top of that, they also used shape information. So this here critical is a square. Warning is a triangle. OK state is a circle. So even if I cannot differentiate red from green, I can see the shape and see, okay, this is square and this is my circle. And then they didn't stop there, but they triple-coded things by using symbols, iconic symbols. So this one here is the cross, this one here is the exclamation mark, and this is here the check mark. So they actually triple-coded that information. And, I just assume maybe this played a contributing factor to winning that award. So that's something that you can do. But what you should not do is rely on color alone, for the reason that 8% of your target audience will have some sort of color perception deficiency or even blindness. What's also really interesting as a Snapple fact is this one here, which just means that you cannot rely on the fact that people would be able to perceive color information outside of a range of 60 degrees. For red and green, it's actually within 30 degrees. It's just you cannot reliably tell colors in the periphery of your eyes. So if you want to, for example, show something is really, really important and it's happening on a large screen to the periphery, don't use red and say, oh, here's an alarm, but blink it and flash it. That's very, very prominent even in the periphery of your eye. This one here just talks to the fact that any lens, it's just a physical thing, any lens, whether it's glass or plastic or our own lens in our eye, bends light of different wavelengths unequally, so it produces different focal points. And since blue and red lie on the opposite ends of the visual spectrum, it means that you should never bring them close together because you can never see blue and red sharp at the same time. Just physically not possible. But I always see this right and left that people do this, like here this advertisement for this printer. this brother in blue on top of the red background, it really looks fuzzy on the screen because you cannot see both at the same time sharp. So for color and contrast, here's what you want to do. You want to have a safe combination of foreground and background. And you see here, these are good and safe combinations. It's not that you would see red and blue here. It's not a recommended thing. But all these combinations are rather good. This one here talks, and this is a question we have received quite sometimes. Should we base our UI on a dark background or a light background? And obviously there's a lot of aesthetic reasons and, branding and these kind of things involved too. But if you look at, what the research says again, then you would want to go with the right alternative, which is a light background and a dark foreground. Both in terms of if you have people rate the legibility of content and the pleasantness. So people would prefer that over the left inverse way. And the best way to show the text here on the light background is to use black and blue. Why? Because it's dark text and it provides a good contrast. If you actually want to, or somebody holds a gun to your head and says, well, you have to have a dark background, then you want to use green, brown, black, or blue as the background color, and then white is the best foreground color, again, for the reason of contrast. So now let's talk a little bit about text. Why is text treatment important? Because in the end, for line of business applications specifically, most information on the UI is still based on text. And so the right text treatment can improve productivity and user satisfaction, but it could also be detrimental to it. I will show you at least one example where some of those eternal rules of text treatment have been changed recently just because of technical advances. And the other reason is just because there's so much bad stuff on the website, on websites. This one here is the website of the Usability Professionals Association. They just, I think last month, renamed themselves into UXPA, so User Experience Professionals Association. But for the longest time, this was their website, and look at this color contrast here. You may probably not even be able to read this, but it's a link to sponsor some things here. I think was it sponsor job board or whatever. It's hard to read for myself as well. So this is really ironic, not only that the Usability Professionals Association would come up with a contrast like this, but also this is a call for funding. So they will actually want to, get some money for this website. But if people cannot read this, people would not go there. So that's just a call to action to reflect a little bit on text treatment. Number one, text size. ISO standards and other standards give us a hint on, from an ergonomic perspective, what should be the minimum viewing range here that people can actually perceive something. And you don't have the time to go into this, but you can calculate based on this formula here what the actual size in inch or millimeters of an uppercase character shall be depending on the viewing distance. And the viewing distance varies obviously depending on whether you work with a handheld or a regular computer monitor or a projection wall. For a regular computer monitor, you want to have at least an uppercase character. So you measure top to bottom on an uppercase character of 2.33 millimeters, at least. The optimum range is between 2.91 and 3.21, but in most times, we see it around this one here because these are really larger font sizes that take a lot of real estate away. And if you ask what does it mean for, I don't want to talk about pixels because pixels change with resolution. I also don't want to talk about millimeters. Just give me the points. The points is at least 9 points. It should bring you to the safe zone. Optimum zone would be between more than 12 points. Again, most times we see that it's a 10-point on systems. What about font type? For the longest time, there was this rule that says, well, just because of resolution, while you can show these serif types, font types, serifs are those little feet here the extensions on the characters. On a book, you can show those, because on a book you have like 800 plus dots per inch. So you can show these little feet very, very sharply, even for smaller font. But if you work on a regular PC right now, you have a pixel density of about 90 pixels per inch. For very small fonts, it's very hard to show these feet then sharply. So that's why for the longest time people were saying, if you show something on a monitor, use a sans serif font. Sans, it's French and says without. So these are without the feet. All of a sudden, we had the Kindle. All of a sudden, we had the iPhone 4 with Retina displays. These displays provide such a high resolution and pixel density that it's no problem to show this little feet. And we talk about 326 pixels per inch on the iPhone 4. So this is more than we actually can resolve with our eyes. So here, changes in technology have changed that epic rule here. If you work with a Retina, you know that your users will work on a Retina display. It's safe to use serif font types. If not, it's still better to use the sans serif font types. Use of letter cases. We have a question, should we show, for example, on push buttons or paragraphs of text, should we use all lowercase letter cases or mixed case or uppercase? Most human factor specialists say you should use mixed case because the ascenders, which is all the parts of the characters that go up, and all the descenders, which are the parts that go down the baseline, they help you to understand the typical words because, a word is characterized by the ups and downs here. Also, mixed case is nice because it allows you to understand sentence structure better, because if something is capitalized, you know that it's either a name or it's the beginning of a sentence. But I don't want to, tell you. I also want to tell you that there's opposing findings more from the medical field, which say that just purely on the size of the all uppercase letter cases, this is good for people that have visible impairments because it's easier to read for them just purely on the size. But if you do the test and try to read this sentence versus this sentence, you tell me what you think is easier to read. And most people say it's actually the mixed case. And in fact, New York City started in 2010 to replace all their street signs here. They used to be all uppercase, and they all changed them now to mixed case. And it's more than $25 million they spent on that. So there has to be a reason, because they were figuring it's easier to read for people in the car if it's mixed case. The last thing that I want to talk about is alignment of text. Text alignment in menus in our Western culture, where we read from left to right, should always be left aligned. Why? Because it provides an easy scan line here. Eye tracking studies prove that. You do not want to center align things. You also do not want to right align things. Obviously, in cultures where you read from right to left, you exactly do want to do things like this. You do want to right align things, but then again, this whole menu would be placed on the right-hand side. Now, in a form where you have labels and text entry fields or any kind of fields that you would need to value, it's a little bit different of a story. Here, you do not want to left align things because it's not so much about scanning these labels here vertically. It's much more important to associate the label with the field where you have to put in data. For that, you want to right align your labels. This provides a small gap only between label and entry field, and also a very consistent gap because it's the same spacing here. While here you see it can be different depending on the length of your label. This has been shown by eye tracking studies. You see here, if you left align your labels, there's much more traffic of the eye necessary to understand what's going on. While here on the right-hand side, where we have right aligned labels, there's less eye traffic. So again, right aligning things is a good thing. You could also top left align things, so you go on top of your entry field, obviously left aligned, which has the added benefit that you can save horizontal real estate, and it's still safe for text size expansion. If I were to translate this English into like Italian or German, you typically have text size expansions of about 150%, so things get longer. And so this may be a problem here if everything is like planned, on the pixel. Here you can have that, and it doesn't impede it with any other UI element. What you should not do is to align the label here after the text entry field, and also not on the right-hand side, because there's a lot of traffic. First of all, you have to visually go beyond this, read what this is, go back, go left, enter things. It's not good. This one here is rather prominent. You see this all over the place on the web, but it's not the best practice. Why? Because it shows that just purely on the fact that something is in there, even it's just the instruction and you have it in gray or in brackets or whatever, parentheses, people just because something is in there assume that it's already filled out, and they don't even read that, and they just try to submit something, and then you throw an error message at them. The other reason is I have to write over the instruction when I value that field. So if I now want to actually put in my last name, I click on it, I put my last name in, I go to the next field, put my first name in, I go to the next one, and now I may have to, I look back and say, well, was the first field actually last name or first name? Maybe they wanted me to put the first name in the first field. There's no way for you to know that unless you go in and remove your string and then see what the instruction was. Just happened to me the other day when I had to do this on a website. So that's not a good practice. And the last contextual slide here about text orientation. From a human factors perspective, the easiest way we can read things is if the text is horizontal. I mean, there's a reason why in our Western world books are printed that you can read things horizontally. But there are instances where you have to do different things. So for example, here you have a vertically aligned tab structure. You cannot show things horizontally here. You have to do something. Now the question is, what can I do? I can use marquee style, where if I put one letter below the other, or I can rotate my text. People to read something correctly. There's no difference between left or right rotation. But there's a huge difference if you do it marquee style. So the worst thing you can do, it takes really the longest time to read something if you do a marquee text. Here, the response time is the longest for marquee text. That's what you should never do. And that brings me to the summary. Technology does advance very, very rapidly, but we as humans, we stay the same. You see here on the graph, human cognitive capability, it is what it is. It doesn't change. It may change over tens of thousands of years, but hey, computers are 50, 60 years old only, so don't expect that this curve would go up anytime soon. It's very gradual, if any. But the task demand powered by the technology is increasing very, very fast. And so we need UX considerations, human factors engineering, to empower people to really make sense of the systems and to manage complexity. Great UX means make it easy to perceive, understand, act, and get feedback. And on top of that, make it very, pleasant and joyful. So all this is obviously going way beyond what I was talking about in this hour. It goes way beyond just talking about, well, what are we good at, what are we bad at? It's a process. And in that respect, this was just one stepping stone. But I do hope that I could provide some content to you that was informative, that was helpful, and that you can also apply when you now are chartered to do UX design or front-end implementation. Just try out some of the best practices here and see if it's helpful. Thank you very much, and also thank you very much for rejoining the webinar since we had to repeat that. We really do appreciate that, and we'll make the link to this presentation as well as to the other webinars available soon, and then you can review that presentation. Thank you very much. Goodbye.